Hi everyone, my name is Rebecca.bowler and this is a very brief overview talk of the DPhil that I'm offering for start next year. I'm going to go through the slides quite quickly, but feel free to pause them and read the slides in a bit more detail and let me know if you have any questions with the email along the bottom there. So this project is about galaxy evolution in the early universe. So what do I mean by that? Well, if we look at the timeline of the universe on the bottom here, you can see on the left we have the Big Bang. And this was followed by a period known as the Dark Ages, where no stars had yet been born. Around a few hundred million years after the Big Bang, we had the formation of the first stars and galaxies, we think, and it's these sources that are most interesting to astronomers. This project aims to study galaxies in the first few billion years and understand, when they formed, what their properties are, and how they change with time. And remarkably now, galaxies are detected all the way up to redshift 9, which corresponds to only 500 million years after the Big Bang. And on this diagram on the top, you can see the age of the universe, and on the bottom you can see 1 plus redshift. And this tells you the redshift of the galaxy we measure. And it's really looking at redshifts greater than 4 or so, we can probe the first few billion years of the universe. So what do we know about these early galaxies? Well, looking at them with some Hubble imaging shown on the top right, we see that they are very irregular and compact sources, so only 1 kiloparsec across or less, much, much smaller than galaxies today. From looking at their colours shown on the bottom right via this parameter called beta, we know that they're very blue sources dominated by young stars, which with a very little chemical enrichment, as you might expect from the very first generation of galaxies. Despite these advances, there are still many challenges and open questions, and these are the questions the broad questions that we're trying to answer as part of this DPhil. So firstly, when and where were metals produced in the universe? By metals, I mean elements heavier than hydrogen and helium. These must have been produced in the early universe. When did supermassive black holes become active? We know that there are some very supermassive black holes already in existence very early on in the universe. How did they get there, and are they common in galaxies or not? And finally, how did the universe reionize? So the universe went through a state change in the first billion years, where it went from being predominantly neutral to predominantly ionized, and it's thought that galaxies produce the ionizing photons to do this, but it's still very uncertain. So this project is based on exploiting data from 2 new facilities coming online in the next few years, Euclid and the Vera-Rubin Observatory. And the reason why these are so important is they're going to give us 100 times the area or more of previous surveys used to study these galaxies. And that means that samples that are currently very small, we only have tens of these rare sources, will become much larger, and we'll have many thousands of which to understand their properties. And in particular, this project focuses on massive galaxies, so the more rare, massive sources that formed after the Big Bang and their properties. So Euclid is a near-infrared survey satellite. It's focused in particular looking at the highest redshift sources that we can, redshifts greater than 7, corresponding to less than 800 million years after the Big Bang. On the other hand, Rubin is an optical survey telescope on the ground, and its focus is more on slightly lower redshift galaxies, where in particular we can get very large samples of such sources that are still probing very early in the universe's history. The plot on the bottom shows you the transmission functions of the different photometric filters that are available with these telescopes. And you can see that by combining the Rubin optical filters and the Euclid near-infrared filters, we're able to get a good handle on the spectrum of the source across a wide redshift range. So in terms of a rough project outline, the first few years will be focused on building up your expertise such that you're the expert in selecting very distant galaxies from these data. And this is a little movie which demonstrates the kind of techniques that we use to find distant galaxies. So if I play it, you can see the model spectrum of a galaxy being redshifted through the photometric bands. These are from Hubble, but it's the same idea with these other telescopes. And what you can see is that the source looks very different as it's redshifted through these bands, and we can use the colours via model fitting to select these very distant galaxies by what's called the Lyman break technique. So The early years of the project will involve getting up to speed with all the data, forming the first sample of sources from these data sets, and quantifying this in what's called the luminosity function of galaxies. And this is the most fundamental measurement of galaxies we can make, which is just telling you the number density as a function of luminosity, as shown on the left here. As you can see, as we go to brighter galaxies, the error bars get larger and larger, and the uncertainties get larger. And it's where the question mark is that this project will make a big impact, giving us the first measurements of the number densities of the most rare and exciting sources within the first few billion years. And once we have this measurement, we can then compare to simulations. What does this mean in terms of astrophysics? And in particular, identify the effects of things like gravitational lensing, active black holes, or mergers on the number of galaxies that we see. So with this strong basis in understanding the data and understanding the selection of galaxies, the latter parts of the PhD are a little bit more flexible depending on interest. So one option is to look more at the statistics of galaxies, the properties of galaxies, in particular the stellar and dark matter masses and environments. And on the left, this shows you how we can do detailed model fitting to data to understand the galaxy properties like star formation rate, stellar mass, and so on. On the right is a demonstration of the clustering of sources. If we measure the clustering on the sky, this gives us an estimate of the dark matter halo mass in which they reside, which is a really fundamental measurement to be compared with the stellar mass, for example. Another option for the later years, again, depending on the particular interest, is to get more involved in follow-up imaging and spectroscopy. So the sources that the project you will find during the project are going to be fantastic for following up because they're going to be very bright and massive, and we want to know a lot more about them from multi-wavelength follow-up. And so the idea is that you would lead some proposals yourself and also work on existing data that we have in the group to get a real multi-wavelength view of these galaxies. So an example of what we can do here is shown by these different telescopes that we could apply for. And on the bottom left, this is the white contours show you the direct detection of dust emission in a galaxy 800 million years after the Big Bang. And this is telling us that dust exists then, which is really exciting. And on the bottom right is a demonstration of the information you get from spectroscopy. The top spectrum is from an object dominated by an active black hole, and the bottom spectrum is dominated by star formation. So there's a lot of information that can be obtained via follow-up spectroscopy. So this aspect of the project would involve, as I said, applying for telescope time, but also data reduction and really becoming the expert in many different wavelengths of observations. Okay, so that's the end of this brief talk. As I said before, please send me any questions you have via email, and best of luck with your applications. Thank you.